Welcome back, everyone. In this second part of our electrochemistry explainer, we're diving into two huge topics for your Class 12 exams. We're talking about electrochemical cells, and of course, the super important Nernst equation. So, let's just jump right in.
Okay, so first things first. Pretty much the whole field of electrochemistry kicks off with understanding this one fundamental device, the galvanic cell. I mean, what's its job? It's all about taking the energy that's locked up inside chemical bonds and turning it into electricity we can actually use.
Okay, take a look at this diagram. It might seem complex, but the main idea is actually pretty simple. You see, a galvanic cell is clever. It takes a redox reaction and splits it into two parts, what we call half cells. So you've got oxidation happening in one beaker and reduction happening in another. By keeping them separate, we make the electrons take the long way around through an external wire. And guess what? That flow of electrons is what we call an electric current. Now, I know it can be tricky to remember which electrode is which, especially when you're under pressure in an exam. So I've got a little trick for you. Just remember the word lone. It's an acronym that stands for left side, oxidation, anode, negative charge. Seriously, this little word tells you everything you need to know about the anode in a galvanic cell. And the cathode? Well, that's just the opposite of everything else. Easy, right?
The Daniell cell is like the superstar example you'll see in every textbook, and for a good reason. It's a classic. Here's what's happening. You've got a zinc electrode and a copper electrode. The zinc anode literally starts to dissolve, and as it oxidizes, it releases a stream of electrons. Those electrons then zoom through the external wire all the way to the copper cathode. And what do they do there? They find copper ions in the solution and reduce them, plating solid copper right onto the electrode. It's a beautiful little system.
Okay, so obviously chemists got tired of drawing this whole setup every single time they wanted to talk about a cell. So they came up with a shorthand called cell notation. It's super useful. See that single vertical line? That just shows a boundary between two different phases, like between the solid zinc metal and the zinc ions dissolved in water. And that double vertical line smack in the middle, that's our salt bridge, connecting the two halves.
And let me tell you, that salt bridge is not just for show. It's absolutely crucial. Think about it for a second. In the anode half cell, we're creating tons of positive zinc ions. The solution is getting way too positive. Over in the cathode half cell, we're using up positive copper ions, so that solution is getting way too negative. If that charge builds up, the whole reaction would just stop. The salt bridge is the hero here. It lets ions flow between the two sides, keeping everything electrically neutral so the electrons can keep flowing. Without it, the battery would die almost instantly. So we've established that electrons flow from the anode to the cathode. But have you ever stopped to wonder why? What's the actual force that's pushing them along that wire? Well, the answer to that question has a name: electrode potential.
The easiest way to think about it is like water pressure. Imagine you have two water tanks at different heights. Water will naturally flow from the higher one to the lower one, right? Electrode potential is kind of like that, but for electrons. Each half cell has a certain electrical pressure or tendency to either push electrons away or pull them in. The overall cell potential, the thing we measure in volts, is just the difference between those two pressures. And by convention, we always calculate it as the potential of the cathode minus the potential of the anode.
Okay, so if we want to compare different kinds of cells, we need to make sure we're doing it fairly, right? It's like comparing race cars. You have to test them on the same track under the same conditions. In chemistry, those standard conditions are 1 molar concentration for any solutions, 1 bar of pressure if there are gases involved, and a nice room temperature of 298 Kelvin. When we measure the potential under these exact conditions, we call it the standard electrode potential. And you'll see it written with this little circle symbol, which we often call not or standard.
All right, but this brings up a bit of a problem. You see, a voltmeter can only measure the difference in potential between 2 points. It can't tell you the absolute potential of just one half cell. It's like trying to measure the height of a mountain. You need to know where sea level is, right? So in electrochemistry, we needed to invent our own sea level, a universal reference point that everyone in the world could agree on.
And that reference point is called the standard hydrogen electrode, or SHE for short. It's a really clever little setup. You've got a platinum electrode dipped into a 1 molar acid solution, and then you bubble pure hydrogen gas over it at 1 bar pressure. And here's the brilliant part. By international agreement, scientists just decided to define the standard potential of this specific half cell as exactly 0.00 volts. That's our baseline. That's our sea level. So this is the standard notation for the SHE, and it's a good one to memorize for your exams. The beauty of this is, now that we have our 0 point, we can take any other half cell, connect it to the SHE, and measure the voltage of the whole setup. And since the SHE is 0, the voltage we read on the meter is, by definition, the standard potential of that other half cell. Problem solved.
And this brings us to a super important formula for calculating the standard potential of any cell. It's simply E cell equals the standard potential of the cathode minus the standard potential of the anode. Now here is a massive exam tip, so listen up. When you look at values in a data table, they will always be given as standard reduction potentials. You just plug those numbers directly into this formula. Don't flip the sign for the anode. The minus sign in the equation already takes care of the fact that oxidation is happening there. It's a common mistake, so don't fall for it.
Okay, so what happens when we use the SHE to measure the standard potentials for a whole bunch of different half reactions? Well, we can take all that data and arrange it into a ranked list. And this list isn't just a boring table of numbers. It's an incredibly powerful tool that lets us predict what will happen in a chemical reaction. We call it the electrochemical series.
And here it is. The electrochemical series is basically a league table for half reactions, ranked by how much they want to be reduced. Way up at the top, with really high positive E0 values, you have the champions of reduction. Like fluorine, it will do anything to grab an electron. And way down at the bottom, with big negative values, you have things like lithium, which are desperate to lose electrons and get oxidized. So just by looking at where two things are on this list, we can predict which one will oxidize and which will reduce, and whether the reaction will even happen on its own.
All right, let's shift gears. We are now moving into what is, without a doubt, the most important part of this chapter when it comes to solving numerical problems. This is the one you absolutely have to get your head around. I'm talking about the Nernst equation.
I mean, let's be real for a second. Those standard conditions we talked about, 1 molar, 298 Kelvin, that's a perfect laboratory scenario. But in the real world, your battery doesn't care if the temperature is perfect or if the concentrations are exactly 1 molar. So what do we do then? How can we calculate the cell's potential when we're not in those ideal conditions?
Well, a scientist named Walther Nernst came to the rescue with this absolute masterpiece of an equation. What it does is brilliant. It takes the standard cell potential, our perfect world value, E0 cell, and then it adjusts it for the real world. It has a correction factor that accounts for the actual temperature and the real-time concentrations of reactants and products, all bundled up in that term, Q, the reaction quotient.
Okay, let's break this equation down, because you have to know what every single piece means. E cell is the real-world potential we're trying to find. E star cell is our starting point, the standard potential. R is the good old gas constant, and T is the temperature in Kelvin, always Kelvin. Now N is super important. That's how many moles of electrons are being transferred in the reaction. You get that from the balanced equation. F is the Faraday constant, a value that connects coulombs of charge to moles. And finally, there's Q, the reaction quotient. Just think of it as a snapshot of the products over reactants concentrations at that exact moment.
Now, that formula looks a bit intimidating, I get it. But here's the good news. For most of your exam problems, the temperature will be set at 298 Kelvin, which is 25 degrees Celsius. Because of that, we can plug in the values for R, T, and F, and also convert the natural log to a base 10 log, which is easier to work with. When you do all that math, all those constants just boil down to this one magic number, 0.0592. And that gives you this much, much friendlier version of the equation. This is going to be your best friend for calculations.
And the Nernst equation doesn't just stop there. It gives us this incredible bridge over to thermodynamics. Check this out. The standard Gibbs free energy, delta G naught, is directly tied to the standard cell potential. But look closely. See that negative sign? That is the most important part of this equation. Remember from thermodynamics that for a reaction to be spontaneous, delta G has to be negative. So for that to happen, E cell star must be positive. It's a perfect connection. A positive voltage means a spontaneous reaction.
And we can push this connection even further. We can also relate the standard cell potential directly to the equilibrium constant Kc. You know, that number that tells us if a reaction prefers to make products or stay as reactants? It makes perfect sense. A big positive E cell means a very spontaneous reaction, which means you're going to make a ton of products. And that means you'll have a huge value for Kc. It all links together.
So, all this talk about spontaneous reactions, where do we actually see them in everyday life? Well, unfortunately, one of the biggest examples is something we'd rather not see: corrosion. Yeah, the rusting of your bike or car is basically a tiny, unwanted galvanic cell. Little patches on the iron surface act as the anode and cathode, and since the overall E cell for rusting is positive, it just happens, all by itself. But the cool thing is, by understanding the electrochemistry behind it, we can figure out clever ways to prevent it.
All right, let's do a super quick recap of what we've covered. We started with the galvanic cell, our device for turning chemical energy into electricity. We figured out how to calculate its standard potential using the SHE as our 0 point. And then the star of the show, the Nernst equation, let us calculate the potential under any conditions and connect everything back to thermodynamics with delta G and Kc. My final piece of advice: master these formulas, but more importantly, practice, practice, practice the numerical problems. That is truly the key to crushing this chapter on your exams. You've got this. All the best.